Okay, so welcome back. We are in the last section of chapter 1, and bear with me, I want to make sure my mic is on. It is. So we're going to discuss an approximation technique known as Euler's approximation method. For those of you who know me, who have had me before, you have heard me discuss that prolific and amazing mathematician that is known as Euler, but I will spare us from discussing my favorite mathematician at this point. But let's recap. So recall that we were looking for solutions to differential equations, right? We discussed that solutions can come in the form of a general solution or a particular solution. So geometrically, take a look at my orange curve here. A general solution would basically be a family of solutions, right? One of infinite possible solutions. Whereas a particular solution would be the exact solution that we were looking for. Now, for Euler was willing to accept some error, okay, using this approximation method. But the goal was for Euler to approximate this solution, right? This orange curve. So what you and I let's kind of put our our caps on, our math caps on. Let's kind of go back in time a little bit. Let's pretend that we are Euler for a second, and the goal, right? The goal is to find the equation of this orange curve. That would be the true particular solution to a differential equation. Now, so we don't have that. If we had that, there would be no need for this approximation method because we already have the solution. So what do we have? So this is what we have. So what we do have is a single point on our solution curve. Right? So we know one particular point, x at x sub 0, y sub 0. Now you could think of it as, or let me read this second point, then I'll try to give you an analogy. So we know one point on our curve, and in addition, we know the slope, right? The rate of change at that point on the curve. You can imagine that if you were driving in a car and I knew I might not have the position function that would be able to tell me where you will be in 1 hour or 2 hours, but the information that I do have is I do know how fast you are traveling at some particular location, right? So let me kind of draw this tangent line, right? Because we know that slope of that tangent line at that point. Now, okay, you with me on what we have? We have a point, we have a slope. Now, any Algebra 1 student, if I give them a point and a slope, right, couldn't you find me the equation of a line? Right, that's fairly easy to do with a point and a slope. So it would be fairly easy to figure out the equation of this line here. All right. And now, what is our goal? What do we actually want? So our goal is to find a second point on the curve. We have one point. It would be really nice to find a second point on that curve. How do we do it? Or how do we attempt to do so? So let's kind of zoom in a little bit on this graph. And let's see if I can unpack Euler's technique here. So remember, what we have is x sub 0, y sub 0. What we want is we want a new point, x sub 1, y sub 1. Okay. So let's start with x sub 1. Now this is fairly easy. So to find the next point on the curve, what we're going to do is we're going to, from x sub 0, we're going to travel some small distance, h. So please assume that we've zoomed in, right? We've zoomed in really, really close for you to even look at this graph. But what we're going to do is we're simply going to move a distance, and that distance is going to be some distance h. All right, so we're going to move some distance h. All right, now at that point we've arrived at a new x position, and of course this new x position would just be where we started plus h. Agreed? Right? If this is you standing here, if you took a 2-foot step, then h would be 2. So depending on where you started, your new position would be where you started plus 2. Okay, so x sub 1 is simply going to be x sub 0 plus h, right? And again, we're going to let h be very, very small. All right, so now that we're here at this new x position, we are going to rise until we hit what? Well, it would be nice to rise until we hit the orange curve, right? But we don't have that. We don't have the actual solution. So what we're going to do is we're going to rise until we hit this tangent curve. Right? So we would be rising until we hit this new tangent curve. And of course, there's a little bit of error, right? We're not exactly at that particular solution, but you can see that as h I think you can agree with me, these curves are fairly far apart here, but as we get closer, that distance is decreasing, right? So in other words, the smaller h is, the closer you will be to the exact curve. So, okay, so now how do we find, from here, what would be this new y position? Well, of course, it's going to be y sub 0 plus, right? So we started here, and we think about rise over run, if you will. Our run is h, and what is our rise? Well, our rise is going to be y sub 0, or you could say the total y value is going to be y sub 0 plus. Now, how do we get to this new position? Well, it's just simply going to be h times the slope of the line. Now, for right now, I'm just going to write h times m. I don't really like that notation. I'm going to get rid of that m in just a second. Now, what we're going to do is, so when we think about us finding the equation of that tangent line, well, that equation of that tangent line generates the slope, right? There is, a line, anything linear has the same slope throughout the line. So the slope of that line, right, or we'll just use calculus notation, y prime, is going to be equal to f of, now for our purposes, it's going to be f of where we started, x sub 0, y sub 0. So let's now go ahead and bring that down here. So it is h times y prime, or h times f of x sub 0, y sub 0. Okay, so really we're using h, but if you know anything about differentials, this is the same language of differentials. And I think it's going to be best to just do one, okay? So we want to use Euler's method to approximate a particular solution. Now hold on. So let's think about what we have. Remember how I said that you would have a point and you would know the slope of a point, right? Now if you know the slope, if you have a point and a slope, you can have a y equals mx plus b type of equation, right? So in this particular example, we have y prime is equal to x minus y. That's given. We also, so given the starting point 0, 1, so this is our x sub 0. This is our y sub 0. Let's go ahead and carry on from, I'm going to go back and copy and paste here. Oh, I didn't want that. Let's try not doing that. How about I just rewrite it? So remember, x sub 1 is equal to x sub 0 plus h. Y sub 1 is equal to y sub 0 plus h times f of x sub 0, y sub 0, which basically is just a way of evaluating f at the given point. So let's use this right here. This is the formula that you need. This is Euler's approximation method. Let's go ahead and use that to find x sub 1, y sub 1. Okay, now the only last thing is you need to choose your value of h, or in this particular case, h has been defined for you. So we're going to use a value of 0.1 for h. So, okay, so in h is equal to 0.1. Okay. So this is, let's go ahead and start this. I think you'll agree this is fairly easy. So x sub 1 is going to be x sub 0 plus h. Well, x sub 0 is 0. So this is going to be 0 plus h, so 0 plus 0.1. All right, and now let's go ahead and approximate y sub 1. So y sub 1 is going to be y sub 0, which is 1, plus h, which is 0.1, times what? Times f of x sub 0, y sub 0. So let's go ahead and do that off to the side here. F of 0, 1. All right, well, in this case, f of 0, 1 is just simply going to be, let me go ahead and make sure you understand. So y prime is equal to x minus y. We are simply taking 0, plugging it in for x, 1, plugging it in for y, and what do we have? We have the slope at that point, which is, as I said, what we had. So the slope, so in this particular case, this would just be what? This would be 0 minus 1. So let's write that 1 plus 0.1 times 0 minus 1. And now let's go ahead and do a little bit of arithmetic here. So x sub 1 in this case would be 0.1. And y sub 1 in this case would be, 0.1 times negative 1, 1 plus that. So that would be 0.9. Okay, so x sub 1 is equal to 0.1. Y sub 1 is equal to 0.9. Now, I'm not going to do so, but on a test, I could ask you to use your Euler's method to approximate a particular solution. I could simply ask you to find me a second point. Now you would be starting at x1, y1. You would be using the same h value. See if you can find x sub 2, y sub 2. So if you would like, it's up to you. If you'd like to pause the video, see if you can use this new starting point. Okay, and the same h value, and see if you can find another point on the curve. I'll go ahead and give you that solution. So x sub 2 would be 0.2, and y sub 2 would be 0.82. So back to where we were. So remember, we are trying to approximate this orange curve, which is our real, true, particular solution to the differential equation. And we're doing okay. So we have 1 point on our curve, and we're starting to approximate other points that are on the curve. So what does this mean in terms of exact solutions? Well, in due reality, let me go ahead and tell you what the actual particular solution to this is. You know, as we get closer and closer to this true curve by letting our distance h be approach 0. But look, this is the exact solution. Now, all of this should tell you that going from numerical approximations, which is what we're doing here, these are just numerical approximations, going from numerical approximations to exact equations is nearly impossible, right? The ability to generate this from those tiny approximations would be nearly impossible. However, as long as you are okay with some error, then Euler's approximation method, it works wonders. It works wonders for these types of differential equations. So we're going to conclude. Chapter 1's relatively short. I think you'll agree. Not too bad for an intro to DiffEq. It's going to start to get interesting in the next section. So the next section is when we're going to start trying to solve differential equations, right? So this chapter was, hey, here's a potential solution. Can you verify that it is a solution? That's how we started. Then we went through some approximation techniques, slope fields, numerical methods, etc., etc. Starting in the next section, we'll start with our very first method, which is going to be the method of separation. And I will see you there.